Hello, everyone. It's my pleasure to be here with you talking about AI in healthcare. Let's go straight to the point. There are many ways of trying to explain what AI and machine learning mean, and there are many ways to put it in front of non-experts like myself. I consider myself just someone who is interested into this field. And for me, the best way to put it comes from Google Translate. And I've been using this metaphor for a few years because if you think about it, Google translates every single language in the world, or almost all of them, but it doesn't know anything about languages. It doesn't know anything about syntaxes, nothing about grammar. However, it can do it, right? And why? What is the reason? The reason is that it has seen so many cases, so many examples of how things are said in English, and in this case in Chinese, that it can provide the right answer even though it doesn't know what it's talking about, right? The reason is that it learns by cases, it learns by examples, by repetition, and that is basically what machine learning is. A few years ago, some smart people learned the way of making computers not just being programmed by rules, but instead being able to learn by repetition like we do as humans, which we call pattern recognition. And sometimes we even call it intuition. But that's the main idea. Machine learning would be about giving machines, instead of giving them rules, giving them a set of solved problems so that by themselves, that's the key, that's the difference, they can infer the rules. And that comes with a huge advantage, huge benefit, which is even when it's the first time they're seeing a problem, like we humans can do, they can solve it. So computers until 2012, more or less, they couldn't do this. They were programmed by rules. The problem was exceptions, and there are exceptions all the time. But now we have these things that can learn by pattern recognition, by repetition, and they can adapt to new cases, even if it's the first time they're seeing them. This is very powerful, and it explains why AI is exploding in the world. There are so many cases we could stop through, but instead of that, we go straight forward to healthcare and medicine. And I like this example where two professors of medicine, they are kind of joking, and one of them says, look, this is so much the case that we don't learn by rules, we learn by repetition, that I tell you that the pigeons that I use to study this in data science, in machine learning, will be able to tell malignancy in pathology slides or in CT scans better than your residents, than your medical students and residents. And he is right, and he proves it, and they publish it together because it's what it is. We learn by repetition, not only humans, but also pigeons, and being able to transmit this ability to computers has been something genius that is really shaping and changing the world. Because we're not just getting to a point where computers can do the same that we can do. If that was the case, this wouldn't be so interesting. What is interesting is that they can go beyond. They can see things that we cannot see, right? This is what Eric Topol, which is probably the biggest authority in the world in this field of AI and medicine, calls the eyes of the machine, in the sense that you can give it, for example, an ECG, and it can see things that we as cardiologists, as neurologists, we wouldn't be able to see there. Not only an anemia, but gender, but cardiac arrest, but whatever happens that would be invisible to our ability to correlate and also associate variables. But these models are not about normal statistics anymore. They're not about regression anymore. It's about statistics powered by computation, by programming, and they can go beyond in finding those correlations. And I like to put this into two main tasks, which would be classification and forecasting. And you'll see why I make this distinction. Because on one side, you have classification, where maybe facial recognition would be a great case. It can classify faces better than our visual cortex can. That's why many people are using this, police and so on. But you can also take into consideration the timeline. And you can think about forecasting in the sense of predicting who from these teenagers will be a top fashion model, so that these agencies will invest in them. And it works. It works better than doing it with experts. And the reason why I'm including this is because in medicine, it's not very different. You will go from classification. For example, I give you fundoscopies, and as in this case, this is Google DeepMind in 2016, pretty famous study. It can classify who has a diabetic retinopathy or who has a kidney disease, but you can also play with forecasting. You can guess before it happens in the timeline who will have a diabetic retinopathy, or like this nature shows, who will have a certain cardiovascular risk attending to fundoscopy, something that we as humans would never be able to do. And the reason why I make this distinction is because I think it's important. One thing is classifying, which in medicine we would call diagnosing, and that's nice. We see so many cases related to screening, to classifying, to everything related to efficiency in healthcare would be related to this. But what is most shocking for me is the second part, the latter, which talks about the possibility of scoring the risk better than we could with classical statistics, because this is ultimately what we call precision medicine. So it turns out that we've been talking for a long time about precision medicine, but precision medicine would never be a fact until we actually had AI to put it in practice. Now we can make it a reality because we go beyond classical regression. And there are many cases that are out there. We're not going to do any literature review, but something that is changing is the idea that until now we've seen cases where we give the machine learning system a certain data layer, like genomics or clinical variables or proteomics or radiology, whatever, ECG, doesn't matter. But now we're seeing the first trends where in the last years where it's about combining, about merging different data layers. So it's fundoscopy and genome, and you predict macular degeneration. So it's CT scan and health record, or it's radiology and pathology and genomics, and you predict who will respond to anti-PD-L1 in non-small cell lung cancer patients. So that's the idea, and it has a very specific name, which maybe we can remember. I don't like names very much, but in this case, I think it's important to keep it in mind. Multi-model, the idea that now we're going to jump into a new era of AI with multiple data layers, and that increases the precision of those classification and forecastings. So that's why many institutions in the world, hospitals, public, private, are trying to catch up with this idea of creating these data lakes that are multi-model, because people have great ideas, but they need the infrastructure to run their data science or machine learning projects. And this is what the CIO of Mayo Clinic advises, in the sense of not doing everything the first day, but going step by step. And he thinks that going to images, then to structured information, then to unstructured clinical notes, then to telemetry, then to omics, then to environment is probably a nice way of introducing a better data lake with more layers every time. And that's probably something that all institutions will be following in the next months and years. I'm especially interested in one specific data layer there, which is the unstructured notes, the clinical notes of the doctors, of the physicians, because it's usually a very unsolved problem. So you see the PDFs, you see different file formats, you see a lot of narratives in different languages, but it's certainly a very interesting problem for an AI, a linguistic problem that AI can solve. And that's what I started doing 10 years ago with my team, where we worked, and the idea of generating this ability to transform text into variables, but not just transforming it and that's that, but doing it in a way that is scientific, that is reliable. That's why we created this portfolio of possibilities where we go from de-identifying the information, so removing the personal data, anonymizing the medical records, into running natural language processing models that can go from specific to general by pathology, creating dictionaries by which machines can read information coming from different sites in different countries of the world, and we can structure that into actual databases with no human effort. And that allows us to jump into those data lakes, which ultimately end up into registries. That's the way to follow, and that's what we're helping more than 200 sites in 13 countries around the world with actual publications and studies along the way. But this panorama that I'm trying to display has a few problems, of course, and limitations. So if you look at those fundoscopies we were talking about and diabetic retinopathy, when they put it in practice in the United States, it got approved by the FDA, and now we have actual AI in grocery stores and supermarkets in the US diagnosing and referring the patients. But the same algorithm, they put it into other countries, they published it in Indonesia, India, and so on, it didn't work that well. Why? Well, because we know that things require real life and validation. And that's where, for a few years, we have been witnessing in the editorial journals and so on, of the journals and so on, how we were a bit delayed in regards to proving that AI works in real life. But now this is changing. That is the current map of clinical trials running AI across different countries and specialties. Maybe as an anecdote, the biggest clinical trial we've seen so far took place in Sweden with 30,000 women for mammogram. Of course, it was positive. And at the same time, the journals, they already have their, let's say, checklist that you have to prove that you did well in terms of internal and external validation to be sure that your article gets published. So this field of proving, of evaluating the AI is really evolving very fast. We have now tools to be sure that what we're reading is properly done. This is something new that we didn't have a few years ago, but now it's happening. It's probably the stage at which we are right now. So that's the idea. We have to ask the right questions. This is an article a bit before the pandemic. By taking pictures of people, it could correlate, where we would never be able to do it, and tell us who has an arrhythmia, atrial fibrillation. But the question is, why? Why do you want that? And that is probably what we'll have to take care about, because the technology, the methodology is already in place, it's ready, but we are the only ones who can ask the right and needed questions. That's what I learned, because as Picasso very widely put it already in black and white, long time ago, computers are useless. At the end of the day, they can only provide us with answers. So that is my team at Savannah, the ones in charge of structuring all the information from sites around the world and creating automatic registries. And I write an email every week. You read it in 1 minute, and it gives you a summary of what is happening in this intersection of clinical research and AI. And I strongly recommend you to sign in, because the day you're not here, the day you miss a lesson. So thank you very much.